Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Benders Theory. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Jacques Benders was a Dutch mathematician and Emeritus Professor of Operations Research at the Eindhoven University of Technology. In 1963, he was the first professor in the Netherlands in the field of operations research, and was known for his contributions to mathematical programming. He retired at the Eindhoven University of Technology on May 31, 1989. Benders studied mathematics at the Utrecht University, where he later also received his Ph.D. in 1960 with the thesis entitled Partitioning in Mathematical Programming under supervision of Hans Freudenthal. Late 1940s had started his career as statistician for the Rubber Foundation. In 1955 he moved to Shell Laboratory in Amsterdam, where he researched mathematical programming problems concerning the logistics of oil refinery. He developed the technique known as Benders Partition, also called Benders Decomposition, and used the results in his doctoral thesis. J.F. Benders' birth on 1 June 1924, died in Eindhoven January 9, 2017. Benders Partition, or Benders Decomposition, is a technique in mathematical programming that allows the solution of very large mixed linear programming problems that have a special block structure. This block structure often occurs in applications such as stochastic programming, when the uncertainty is usually represented with scenarios. In 1962, J. F. Benders published his seminal theory and the paper Partitioning Procedures for Solving Mixed Variables Programming Problems, Oriented to Optimization of Mixed Integer Problems, MIP. Benders theory, BT, has been the origin of multiples methodologies oriented to solve large-scale problems, related with stochastic complex combinatorial and/or dynamic systems. BT is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. For the editor of this conference, Benders theory is as important as the simplex method, created by Dantzig. Since its formulation in 1962, the researchers in Benders theory, BT, have proven that BT is an effective methodology to solve complex problems that cannot be solved using only best basic optimization algorithms, like Plex, Gurobi, Express, etc. Algorithms based in Benders theory can solve NP-hard problems in reasonable time. BT is a mature methodology that is in the accelerated growing phase. The variations and extensions of BT have come to cover practically all types of mathematical optimization problems. There is a big gap between the research in mathematical programming and the application of the large-scale methodologies in real-world solutions, and BT is ready to grow hand with parallel computing and the new concepts of parallel and distributed artificial intelligence. The growth of parallel optimization-oriented technologies has been significant over the past 2 decades. The image presents the growth of Benders theory from its inception in 1962 to 2016. The green bars, based on a visual projection, presents the expected growth in these years, which is exponential. On the other hand, the speed increase provided by large-scale theories is significant. The table provides information on various types of problems, solved with several variations of Benders theory. The column time ratio solver/Benders presents the relationship of solution times for different sizes of problems. The content is Benders times faster. Benders theory is presented in several conferences, which are grouped into Part 1. Benders, Theory, Variations, and Enhancements. This conference is divided in several videos. Part 2. Dynamics and Stochastic Benders Decomposition. Part 3. Generalized Stochastic Dual Dynamic Programming, GSDDP. Implementation and Electric Sector Applications. The diagram presents the experience as a researcher and entrepreneur of mathematical programming of Jesus Velasquez Bermudez, director of the Large-Scale Optimization Technologies Program. Theory of Benders. Framework. In 1962, J. F. Benders published his seminal theory, oriented to optimization of mixed integer problems, that has been the origin of multiples methodologies used to solve large-scale problems. The optimization problem may be LP, MIP, NLP, and MINP. The fundamental idea is the partition of a problem into two subproblems, of reduced complexity, based on the division of the variables like coordination variables and subordinate variables. The solution of the original problem is obtained by the coordinated solution of two complementary subproblems. The coordinator linked to the coordination variables, and the subproblem linked to subordinate variables, that depends on the coordination variables. The gray area represents the original feasibility zone of coordinator problem. The master problem selects values of the coordination variables and sends them to the subproblem. The subproblem provides information to the coordinator by the dual variables associated with its constraints. The coordinator takes the information from the primary level, the subproblem, and incorporates it in the form of hyperplanes, Benders cuts, limiting the area of feasibility for the optimal solution of the coordination variables. Depending on the solution of the subproblem Y, two types of cuts are generated. Cuts for optimality, when the solution is optimal and feasible, and cuts for feasibility, when the solution is not feasible. Optimality cuts eliminate values of Y that must be discarded because they cannot be optimum, and feasibility cuts eliminate values of Y that must be discarded because they don't permit feasible values of X. Benders cuts represent the costs of subordinate variables as a function of the coordination variables. That is represented by the variable Qy. The algorithm defined by Benders is convergent, and solves the original problem. Through the solution of the coordinator problem, it applies only to linear subproblems. Benders partition theory. This is the original formulation considered by Benders. Benders considers a problem with two types of variables, y-coordinating variables, and x-coordinated variables. Examples of this are y investments, and x operations, y deterministic, and x stochastic, and y first period, and x rest of periods. The type of matrix structure that meets the reference formulation used by Benders is the so-called dual angular. The characteristics of the functions involved in the original problem are: coordinating variables, y vector of decision variables, may be discrete or continuous, fy convex linear or nonlinear function, f0 year vectorial function, may be linear or nonlinear, and fy vectorial function, may be linear or nonlinear. Coordinated variables, x vector of decision variables, must be continuous, C column vector, and a matrix of functional constraints for x. Benders considers the function Qy, that determines the optimum cost associate with x, as a function of y. Qy is determined by solving an optimization subproblem, on the variable x, for a value of y. The subproblem, function of y, must be linear programming 1. The primal formulation of the problem that defines Qy, depends on x and y. Based on the duality theory, this problem can be replaced by the corresponding dual problem, that only depends on y, being totally independent of x. Since the two problems are equivalent, it is convenient to work based on the dual of Qy. A new problem is defined based on the dual of the original subproblem Qy. The dual subproblem can be formulated in terms of the extreme points of its feasible zone. The example presents a closed feasible zone, defined by 5 extreme points πn. Since the dual problem is one of maximization, if are known the total, np, of extreme points πn, that define the dual feasibility zone, it is possible to replace the dual problem with cutting planes, which restrict Qy to be greater than or equal to the objective function evaluated at each extreme point. In the example, np is equal to 5. The original problem can be formulated considering only the variable y, and all the cutting planes associated with the extreme points. In practical terms, this problem has an infinite number of constraints. To solve it, we should have a mechanism to generate extreme points of the dual feasible zone of the subproblem that defines Qy. A structure of 2 levels is established to solve the problem. The first level is the equivalent problem in terms of y, that is designated as the coordinator. The second level is a subproblem for the variable x, that generates extreme points for the coordinator problem. The solution is obtained by exchanging information between the coordinator and the subproblem. The coordinator proposes values of y, and the subproblem generates dual variables π. If the subproblem is solved until optimality is achieved, the generation of cutting planes proposed by Benders converges to the optimal solution of the original problem, without having to generate all the extreme points of the dual feasible zone of the subproblem. However, any dual feasible point π may be used to constraint qy, but it may do not reduce the feasible zone, and it is possible that the Benders procedure don't converge to the optimal solution. Benders cutting planes generation. Now, the process of generating cutting planes is studied. For this it must be analyzed how the feasibility area of the coordinator problem evolves during the iterative process. As a starting point, it can be assumed that the coordinating problem is solved without cutting planes, since there is no previous information. If the optimal solution of the subproblem for a value of y is obtained, an optimality Benders cut is generated. It eliminates values of y that must be discarded, because they cannot be optimum. This process will be performed for each iteration k of the algorithm. Initially there are no cutting planes, and the first iteration will generate the first cut, reducing the feasibility zone of the coordinating problem. This implies that the coordinator will grow in constraints, as the number of iterations increase. Therefore, this process must be controlled, considering that there is a limit to the number of cuts that can be active at any given time. In the case that a feasible solution x does not exist for the subproblem, must be used the Farkas's theorem to generate the following cutting plane. 0 greater or equal than omega k multiply by b minus fy, where omega k corresponds to extreme ray of the feasible dual zone. This cutting plane is called Benders cutting plane for feasibility. If a feasible primal solution x does not exist, then the dual solution is unbounded. This implies that the dual feasibility zone includes at least two extreme rays, which allow the objective function to take values of infinity. Farkas' theorem establishes the cutting planes based on one of the active extreme rays. However, more extreme rays can be introduced if known. If the optimal solution of the subproblem for a value of y does not exist, a feasibility Benders cut is generated. It eliminates values of y that must be discarded, because they don't permit feasible values of x. This process will be performed for each iteration k of the algorithm. To reach the optimum, Benders' algorithm reduces the feasibility zone of the coordinator problem, until it finds that there are no more cuts to reduce it. Below is graphically how the Benders cut's operating. Let's assume that the optimal solution corresponds to the gray dotted line, formed by multiple cutting planes. The polyline represents the value of the objective function. The Benders algorithm must find the cutting planes that define the optimal point. In the first iteration a cutting plane is generated, as a first approximation. In the second iteration, a new cut is generated, which improves the approximation of the value of the objective function. In the following iterations, new cuts are generated, improving the approximation of the objective function. Finally, the Benders algorithm obtains an approximation equal to the value of the real function. It should be noted that this only occurs in the neighborhood of the optimal solution, since the algorithm does not evaluate values of y away from that solution. Considering the case of minimization, the convergence process is based on the estimation of the difference of two curves, or functions, related to the value of the objective function of the subproblem. Using the value of the objective function of the subproblem, c multiply by x, a real, feasible, value is obtained, which sets an upper bound for the objective function of the subproblem. This is a primal bound. Using the coordinator's information, the estimated value of the objective function of the subproblem is obtained, that is equal to qy. This estimated value sets a lower bound for the objective function of the subproblem. This is a dual bound. The optimality gap is defined based on the difference between the two bounds, and determines the convergence process, which is achieved when the gap is equal to 0. The gap begins at infinity and decreases as the process progresses. The algorithm defined by Benders is convergent, and solves the original problem, if the conditions established for the original problem are met. That is, coordinator, the nonlinear part must be convex, and subproblem, it must be a linear problem. Benders decomposition theory. It is applied when the slave subproblem can be divided into several problems. The mathematical formulation is based on two types of variables, the x that acts as a coordination variable, and the y that include a subscript associated with the concept under which the decomposition is performed. This type of matrix is called dual angular. This is the main variation of Benders theory. There is more than one way to perform decomposition, each of them associated with the type of cut that can be handled. These alternatives are: standard Benders cut, SBC, applies for all kinds of problems. Decoupled Benders cuts, DBC, apply to all kinds of problems. Benders unified cuts, UBC, are applied to the problem family, which are broken down from the point of view of random periods or scenarios. The diagram presents the computational parallelism that allows Benders decomposition. With the problems decoupled and unified, parallel optimization is possible using multiple processors. The standard cut does not allow parallelism, as it considers the slave problem in a monolithic way. Parallelism leads to a significant increase in execution speed. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972. In the book Human Problem Solving wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.